Hello everybody, it's Dr. C. We're getting right down to the very end of the semester, and I'll try to keep this short. I know you're pressed for time and there's lots of stuff going on, lots of stuff to do. We do have a little bit left to do in Chapter 11, a little bit left to do in Chapter 12. So this is some Chapter 12 stuff to get us started. Okay. So looking at this problem, we know molarity. We've already done that. Okay. The problem with molarity is that the concentration is temperature dependent. Okay. So remember, grab a pen here. Molarity, capital M, is moles solute. A good way to start the pre-lecture. Moles solute per liters of solution. Okay? So volume of that solution is going to change with temperature. If we increase the temperature, the volume of that solution will expand. Okay? The molecules of the water or the solution will start moving more and expand out. Okay, so the volume is going to change as we as we change the temperature. If we raise the temperature, the volume is going to increase, and so that number goes up, so our molarity actually goes down. Okay, so the big point here is molarity is temperature dependent. Okay, so there's some situations where we're going to be relying on, say, a change in temperature as part of the calculation. We don't want a concentration unit that changes with temperature. So we need some temperature independent concentration units. And both molality and mole fraction are temperature independent. And we'll look at those after we get molarity. So let's calculate the molarity first. It's a good review for the final. We have 181.4 grams of sucrose in enough water to make 500 milliliters of solution. Okay? So we have grams, we need moles. That's not a big deal. We have volume in milliliters, we need volume in liters. Okay? Nothing new. I did put the molar mass here so you don't have to calculate it, but you might want to double check that the molar mass of sucrose is indeed 342.3. All right, so let's do moles first. 181.4 grams, 1 mole of sucrose is 342.3 grams of sucrose. We set up our units so grams cancel. We're left with moles. Okay, and I come up with 0.530 moles. Okay, I guess we have 4 sig figs. Let's add one more sig fig. 5299 moles. All right, so there's our moles. Volume 500 milliliters. Divide that by 1,000 to get 0.5 liters. So our molarity, 0.5299 moles divided by half a liter. We have 4 figs in that too. I didn't write it. So we're going to carry 4 in our answer. I'm not sure what I just hit. Let me just do the calculation. I hit search. We don't need that. So to 4 sig figs, 1.060 molar. All right. That's good review. You need to know how to calculate molarity for the final exam. So we had to convert grams to moles. We had to convert milliliters to liters. That's good. All right. Now let's introduce these temperature independent concentration units. So let's start with molality. Now molality is given the symbol small m, not to be confused with molarity. Now the nice part about molality is the numerator is the same. It's moles solute. But we don't use volume because that volume is going to change with temperature. So we need a different unit for the bottom. And for the denominator, it's kilograms solvent. Okay, not solution, but just the solvent. All right, so it's a little bit different. So we know the first part. We already have the moles of the solute, 0.5299. So that part's the same. But how the heck do we get to kilograms of just the solvent? Well, the other piece of information that you may or may not have noticed in the problem is you're given the density of that solution. Okay? We have 500 milliliters of solution, and we have its density. So we can get the mass of the solution pretty darn easily. Now that's the mass of the solution. It's still not the solvent. Okay? But we're a lot closer, right? So let's do that first. Okay? So we have 500 milliliters of our solution. And remember, this is solution, not solvent. And it's 1.14 grams per 1 milliliter. That's the density of that solution. Milliliters cancel. And I come up with right at 570 grams solution. All right, so we're closer. We have mass, but it's mass of the solution, which is the solute and the solvent together. We just want the mass of the solvent. So the solution is equal to the solute plus the solvent. We want just the mass of the solvent. I think you probably see where this is going. So the mass of the solvent is going to be the mass of the solution minus the mass of the solute. Right? Because the solution is made up of both components, solute and solvent. If we want the mass of just the solvent, we need to subtract off the mass of the solute. So 570 grams. Do we know the mass of the solute? Yeah, it was given in the problem, right? 181.4 grams of sucrose. That's our solute. So the mass of our solute, or solvent, I'm sorry, so subtracting off the mass of the solute, 181.4. I'm going to carry an extra sig fig here. I think we only had 3 in the density, but let's carry an extra sig fig. Grams solvent. Are we close? Yeah, we're almost there. But we don't want gram solvent. We want kilograms solvent. So again, this goes way back to the beginning of the semester. Can you do metric conversions? I'm sorry. Sometimes I hit something on the screen and it jumps around. Kilo means what? Kilo means 1,000. Grams cancel, and we end up with 0.3886 kilograms. All right, so that was a little bit of work. Nothing difficult. We had to factor in density to get from volume to mass of the solution. And then we had to subtract off the mass of the solute to get just the mass of the solvent. Okay? Now we're there. We have the 2 pieces. We have the moles of solute that we calculated up in part 1, essentially for the molarity. We now have the kilograms. We can now calculate the molality, moles solute, and I believe it was 0.5299 moles, I believe. I should probably scroll up to take a look. Yes. And now we divide by kilograms of solvent, 0.3886 kilograms. And I get 1.36. And I think we only had 3 sig figs in the density, yeah, so I'm only going to carry 3 here. And our units are moles per kilogram. Or we can just write 1.36 m for molal. Not molar, it's a molal solution, not a molar solution. Okay. A lot of times we'll write mole per kilogram because that m could get confused with meters, but if we're talking solution concentration, we should be able to figure it out. All right. Now let's look at our difference in molarity. 1.06, 1.36. Usually molarity and molality are pretty close as long as the solution is not too concentrated. Okay, so this is a 1 molar solution, not overly concentrated, but at higher concentrations, molarity and molality can deviate quite a bit. Okay, if you have a really concentrated solution. All right, so that's molality. And again, the point of doing this is we're going to do some calculations where we need a temperature independent concentration. Okay, and so that's going to be temperature independent because the mass, again, as long as we're not evaporating off our solution, which is what we'd assume, that we have a sealed container, our solution is not evaporating, the mass is not going to change. Moles are not going to change because moles is based on mass too. So those won't change, they're temperature independent. All right, last part, mole fraction. And we want the mole fraction. We could calculate the mole fraction of water, which we can do because this is only a 2-component solution. Once we get the mole fraction of one, it's easy to get the mole fraction of the other. And it's going to be the moles of what you're interested. Well, let's just write it this way. Let's just say we want mole fraction of A. And we have a 2-component solution. It's going to be moles of A over the total moles, which if it's a 2-component solution would be moles of A plus moles of B. Okay, so 2-component solution A and B, the mole fraction of A is moles of A divided by total, part divided by the whole. Well, the same thing for sucrose, right? It's moles of sucrose divided by the total moles. Now this is just a 2-component solution, moles sucrose, moles water. Okay, so mole fraction, it's a fraction, part divided by the whole. All right, and again, this will be temperature independent because moles aren't going to change. Okay, sealed container, moles is mass, right? Well, the more mass you have, the more moles you have. They're not going to change with temperature. Where temperature, volume changes, molarity changes. All right, so what do we know? Well, we've already calculated in the other 2 parts the moles of sucrose, that 0.5299. So we know that. So the only other thing we need to know is moles of water. So where are we going to get that? Yeah, from the mass of water. And we already figured that out. The mass of the solvent, we figured out up here, 388.6. Now I'm going to go back to grams because it'll be easier to calculate moles of water from grams. So 388.6 grams of good old H2O, 1 mole water. Add that up, you should get about 18.02 grams. Might be a little different if you carry more sig figs than I did. Grams cancel. And I come up with 21 point, I'm going to carry 1 extra sig fig for now, 565 moles of water. So take a look at that. How many moles of sucrose did we have? 0.5299. So most of the solution is water. So our mole fraction of sucrose is going to be pretty darn small. Okay? So mole fraction of sucrose. Oh, by the way, this looks like a big X, but it's actually a capital Greek letter. I think that is chi. Is that right? And so that actually has little things on the end of the X, but it's a chi. But I typically just write it as an X. But that's the symbol for mole fraction. Our moles of sucrose, 0.5299 moles. We add up our moles for the total moles, 0.5299 plus 21.565, and that's moles. Moles will cancel because we're going to take moles divided by moles, so mole fraction does not have a unit. Okay. And I get a mole fraction of just 0.02398. And I don't think we should actually, well, yeah, that's probably, we have 4 sig figs, let's carry 4. And there's no unit, so that's our answer. Okay? Now, If you wanted the mole fraction of water, that would be pretty easy because it's just two components. So the mole fractions will add to 1. Remember, this is not a percent. So the 2 mole fractions will add to 1. So you subtract that from 1, and we get, and I don't have any more room on my page, so let me just squeeze it down here. So subtract that from 1, and our mole fraction of water is 0.9760. Okay? And maybe we could carry another sig fig, 0.97602. All right? But anyway, what that says is this solution, if we convert this to percent, is about 2.398% sucrose. The bulk of the solution is solvent, as you might expect for not a super concentrated solution. Convert that to percentage, it's 97.6% water. Okay? In terms of moles. Okay? That's mole fraction. Again, temperature independent. So there are calculations that mole fraction will be used in when temperature is changing. There will be calculations where molality is used where temperature is changing. Okay? There's another, we're not going to do this one, I'm not going to cover this one. It's in chapter 12 of your text. Mass percent is another one you could use as a concentration unit that's temperature independent. Okay? Which is calculated like mole fraction, but it's a percent where it'd be mass of what you're interested in divided by the total mass, multiplied by 100 to get a percent. And again, mass, you're not using volume, so that's temperature independent. So that's another one we could use. All right, I think that's enough. This will get us started. We'll talk a little bit about solutions, a bit more in class on Thursday. We'll do some calculations with osmotic pressure. We'll do some calculations with freezing point depression and boiling point elevation. We'll talk a little bit about vapor pressure. And that'll be it for this semester. So we are almost done. So I will see you on Thursday. Take care.